All right, guys, let's come to order. We do have an abbreviated schedule today, so let's get right to it. Yesterday we did calorimetry. Hopefully you have a pretty good idea what these things are. If you don't, come see me when we run your lab. Again, you can have 15-20 minutes at the end of our little mini lecture to finish up your lab. So what I'm going to talk about is boiling water. If you took some boiling water and you basically put a temperature probe in the boiling water, what's the temperature probe going to tell you? What temperature is it going to tell you? 100 Celsius, exactly. So if you had bought a boiling water, it's going to tell you 100 Celsius. That's great, okay, because that's the boiling temperature of water. But what if it wasn't like a raging boil, blah, 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 blah. What if it was just a simmer? What temperature would a simmer give you? 100 degrees Celsius, exactly. Because a simmer is just a boil that's a slow boil, right? So when you get to 100 degrees, all the additional energy you're pumping into the water is going to a phase change. Does that make sense?
Yeah.
Okay, so we're not going to superheat the water. Once you get to 100 degrees, any additional energy is going to a phase change. Now, consider that. Now consider this thought experiment. If you were the manager at Costco and somebody asked you, what temperature should we set the bag of ice to? The big box with bags of ice. What temperature should we set it to? Should we set it to 0? Or should we set it to -20?
-20.
Why should we set it to -20?
Because then that way as soon as you take it out, it won't even start melting.
Exactly. If you set it to 0, the moment you put it in your car, it would start melting. So they set it to -20, so when you put it in your car on a nice hot day, you don't get a bag of water in the back of your trunk. Okay? So imagine you have a block of ice. It's at -20 degrees. You put it in the trunk. The trunk's like 130 Fahrenheit. Let's say it's 50 Celsius. What's going to start happening to that ice? Is it going to melt?
Not yet.
Not yet, exactly. It won't melt because the melting point of water is 0. Good. So if you were to graph heat added via temperature, it would look like this. This is your -20 degree bag of ice. What temperature is this?
0.
0. So it's going to warm up to 0. Once it gets to 0, now you're at the melting point of ice. Then what it's going to do? If you continue adding ice, or adding what? Adding heat.
Phase change.
Then it's going to, so we warmed it up. Now we're going to have a phase change, where when we're at 0 degrees.
Please pardon the interruption. The announcements will be playing at 9:10. The announcements will be available at 9:10. Thank you.
This class. Maybe at the end of the period. Maybe. Okay, so once you get to 0 degrees, any additional heat's going to go to a phase change. You've got your solid to a liquid. That's your phase change. So you warm up your solid to a liquid. Now, you get to this point here. What's going on during this time here? The phase change. And here, now all of your water is liquid. Exactly, all your water is melted. Now, once you're there and everything is melted and you continue to give it heat, what's it going to do? It's going to warm up. What's the graph going to look like? Yeah, most of you, it's going to look like that. So this is our warming curve again. So we have a warming curve, a phase change curve, and a warming curve. And you warm it up and warm it up and warm it up. Eventually you can't warm it up anymore. What temperature is this? 100 degrees. And what's the line for boiling going to look like? It's going to be a horizontal line again, exactly. Excellent. So boiling, 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 until all of your water has become gas. And then this part, gets gigantic because you can make steam extremely hot. So this one just goes whoo, up into the sky because you can make water steam extremely hot. Ice basically from -273 to 0. Liquid water, tiny little window of 0 to 100. Gaseous water, huge window from 100 to several thousand. Yeah. There is no -300. So absolute 0 is -273 Kelvin, or -273 Celsius, or 0 Kelvin. So there's a lot of theories about what would happen if you were to get something to absolute zero, but as far as we know, it can't happen because matter is made up of a nucleus and an electron or more that has to go around it. If you stop something at absolute zero, that electron can't move anymore. So what happens if you stop the electron from moving? It's possible to just go zooming into the nucleus, but then again, that would be motion. Okay, does this make sense? So this is what a graph looks like if you add heat. First you warm, then you phase change, then you warm, then you phase change, then you warm. The formula for warming we already know, mc delta T. The formula for phase change is ml. This is called latent heat. It is the latent heat constant. It's basically the amount of energy it takes to phase a gram of something. Oh, cool, we got a full boat. Okay. Sure, you wait till Friday to have a perfect attendance. Oh, wait. Yeah, almost one short. Okay, so are we good about this? Okay, now the next thing we want to talk about is enthalpy. Enthalpy is heat energy given off or taken in during a process. And thank goodness we finally have a variable that is the same letter as what it represents, heat. Okay, so enthalpy, H, is the heat energy given off or taken in during a process, during a very specific process. So enthalpy is the heat energy during a specific change, from solid to liquid, from gas to solid, from reactants to products. Okay? It's the heat energy for a very specific change. And because it is a change, we throw a triangle in front of the H. What does the triangle in front of an H mean?
Delta.
Delta, what does it mean? Change in, yeah. So we're talking about change in heat. The enthalpy is a change in heat. Okay. So delta means change, so we put a delta in front of it, means change in. Now, we talked about exothermic and endothermic processes. Exothermic process means the energy goes out of the system. Once again, we are not the system. We are the surroundings. The system is what's in front of you. Okay? We're not it. We're the surroundings. So if energy is coming out of the system, that's an exothermic process. And an exothermic process, it's a negative delta H. Energy is being given off. Energy is coming out of the system. For us, as the surroundings would feel warm. We'd be like, hey, I'm absorbing some energy from that system. But again, you got to think about the system. We're not the system, we are the surroundings. And it should make sense that if an exothermic process has a negative delta H, an endothermic process has what sign?
Positive.
Positive, because energy is going into the system. Into the system. So, as the surroundings, endothermic systems feel cold because we're the surroundings, energy being taken from us going into the system. Now, I mentioned this a while back, that when the universe was created, it loaned all the energy it had to all the molecules in the universe. It loaned out all the energy, but the universe wants it back. So anything that has the universe getting energy back is going to be what's called spontaneous or favored. Okay? Fireworks are spontaneous because they release a lot of energy back into the atmosphere, back into the universe. So anything that releases energy back to the universe, repays the loan, is going to be favored or spontaneous. So exothermic processes are favored. The universe likes exothermic processes. It likes things that release heat back because the universe is like, hey, I loaned you a bunch of energy. I'd like some of that energy back, or I'll break your legs. Give me that energy back, or I'll stick you on this planet and let you destroy it. Okay, next. Molecules have enthalpy of formation. My water molecules have enthalpy of formation. In other words, to put the molecule together, I had to do something to assemble it. Okay? I had to use energy to assemble my molecule. Similarly, the universe has to use energy, or something has to use energy to make a molecule. So molecules have enthalpy of formation. Sometimes it's positive, sometimes it's negative. However, free elements do not. Things that are in their simplest possible state, like hydrogen or oxygen, things in their simplest elemental state do not have an enthalpy of formation because they are the simplest building blocks they can be. So this is one of those things that if you see something in its simplest elemental state, it has a delta H of 0. Remember this. We're going to be using it in a math environment next week. So things in their simplest state, elements like oxygen or hydrogen or copper, have a delta H of 0. They're, how hard is it to make a building block of Legos? Like, what's your model? It is 1 block. I'm done. It's already the simplest block. Okay, questions? All right, give me a thumbs up if you're with me and ready to move on. Put your hand up and wave it around if you have questions. Okay, looks like we're ready to move on. Moving on. One of the things I asked you to do on that little half sheet, this half sheet, was look up some of these enthalpies. Some of you did okay. Some of you just copied somebody who did better than you. Regardless of what happened to you, and it's really obvious some of you copied because you wrote in P for F. There was no P option here. I'm looking at you, second row.
Cheaters.
Yeah. Yeah, whatever. This is why our daily work is only over 30%. But there will be on the quiz. There will be some matching on the quiz where you need to match the enthalpy type to what it is. So these are the enthalpies: heat of vaporization, heat of condensation, heat of sublimation, heat of fusion, heat of reaction, heat of formation, heat of solution, heat of combustion, and that's it.
That's a lot of heat.
It's a lot of heats, and it's not even all of them. There are even more. These are just the ones we're going to focus on. So we need to know what these things are, and are they exothermic or endothermic? So I'll give you a minute or two to scribble these down. Leave a little bit of space to the side to write exothermic or endothermic. Heat of vaporization. Heat of vaporization is the heat energy given off or taken in, you choose, when a liquid becomes a gas. If you think this is an exothermic process, let's say exothermic is pointing away from you, like you're the system now. If you think it's endothermic pointing towards you. So if you were the system and you need to boil, do you think energy would go away from you or towards you? Is it an exothermic process or an endothermic process? What do you think? Toward, away, toward. Looks like the front row's got it. Most of you in the front row are saying toward is toward. Yeah, it's endothermic. Heat of vaporization is endothermic. It's going to require energy to do its thing. So heat of vaporization is endothermic. Condensation is the opposite of endothermic, or opposite of condensation. Excuse me. Condensation is the opposite of vaporization. So heat of condensation is when a gas condenses to a liquid. This is what you feel when you put your hand in a stream of steam and the water condenses on your hand. You're like, oh, the steam has condensed to liquid water. And ouch! So heat of condensation, is it exothermic or endothermic? Exothermic, yeah. Should be the opposite of vaporization. It's exothermic. Sublimation is what we get when a block of dry ice you buy at the grocery store becomes a gas. It sublimates. So does sublimation from a solid to a gas require energy or give off energy? What do you think? Does sublimation require energy or give off energy? Most of you realize it's going to require energy, so delta H should be what sign? Positive. And heat of fusion is the opposite of heat of sublimation. So if sublimation is endothermic, fusion must be exothermic. All right. Now, heat of reaction is just the heat of any reaction. Heat of reaction is abbreviated RXN. It's the heat of whatever, and it can be positive or negative. Heat of formation, so here we go. Heat of formation or heat of reaction is positive or negative, depending on the reaction. Heat of formation is the energy required to make a molecule. Okay. Energy required to make a molecule. Usually endothermic, but sometimes exothermic. So energy required to make a molecule. Sometimes endothermic, sometimes exothermic. Heat of solution. Heat of solution is the heat given off or taken in when something dissolves into its ions. Usually exothermic, sometimes endothermic. Towards the end of the year, we're actually going to be doing a lab where we do just that. We're going to dissolve it. You're like, it got cold. Weird. And heat of combustion. The universe loves making water. And remember, fuel plus oxygen makes water and carbon dioxide. The universe loves making water, almost always exo. All right. One slide left. Then you can use the rest of the time to work on your lab. So, yeah, you've got about 20 minutes. No, maybe 15, like I said. Okay, questions? All right. Now, if you had energy written into a balanced chemical reaction, and delta H is negative, meaning it's exothermic, that means energy is being given off. Would you write heat on the product side or the reactant side? Product side. If something is exothermic, you're going to write energy on the product side. So you would write it like this. This is the burning of 1 mole of glucose. Burning 1 mole of glucose is going to produce 2,870 kilojoules, thousands of joules. It's a lot. It's what keeps us going. Okay. And we would write it this way. Delta H of reaction is negative 2870 kilojoules per mole. Per mole of what, by the way? Per mole of glucose, exactly.